So I've just mentioned that the new homework has been posted. Please collaborate and at your discretion, share with each other what you have done so that when you see the homework 5, you won't be too surprised. Part of it depends on the development that you have from the activity for topic 7. So here is the next stage. So the next stage, we are not doing a huge amount of new calculation yet. Um, but first we need to identify what we have learned before in terms of forming elementary functions versus the new version which depend entirely on series. And so here is 4 examples. I'm going to work through it. And then we'll go to the Laurent series theorem, which is a generalization of Taylor's theorem. But it only is taught in complex variable y. Okay, so we'll talk about that. So let me copy and paste these examples, and then we start work on it. So these are the examples. The first one, my screens are in opposite direction. Okay, maximize it. Example number 1. You have the question to expand 1 over 1 plus z squared in power series about the point z0 equals to 0. Now, if you start with the only machinery that you know from calculus, the likely thing that some people, at least in the class, will try is to do this. So one valid way is to let f of z equals 1 over 1 plus z squared, and then find f nth derivative evaluated at z0 to form the Taylor series about the point z equals z0. And here, since your z0 equals to 0, it's also called a Maclaurin series. And all these names actually do not affect how I actually work on it. It's just a tradition to honor some people who did some work on it. And their work back then, working on this series, have a very different flavor compared to the calculus we learned. So it's just a few names attached to it. And before Maclaurin, before Taylor, Euler knew all of these. So this is not really a surprise. So if you were to look at the derivatives, very soon you get some trouble. Let me write it in red on the side. So f of z is that. So f prime of z, let me not change color. That was not a good advice from last time. So let me carve out a space, do some scratch work. F prime of z is what? F prime of z is quotient rule, okay? So, or chain rule. So this is power -1. So I do -1 outside with an F sign. The original thing to the power -2, like this. So it's on the denominator. And then I have chain rule. So differentiate the denominator function, which is a polynomial, so it's 2z. So clean it up, -2z over 1 plus z squared all squared. Whew. Okay, we survived. But the next step, let's do that again. F double prime of z, I don't know how to make it. So you can use quotient rule. Keep the negative sign outside. Then you have this to power 4. And then copy the denominator. I think my line is not long enough. Let's pretend. Squeeze it in. And then differentiate the numerator, z, minus 2z times the denominator, which is 2z again. So you would discover that on the numerator, you can't actually factorize it. Yeah. Right now you do. You can still factor a factor of z, but in the long term, the coefficients are a little bit erratic. Okay? So if you expand it all, I think you get z to power 5 plus, here you have 2z cubed minus 4z squared plus z over 1 plus z squared to power 4. I believe we don't want to do it. Okay? So the original standard way back in calculus to expand 1 over 1 plus z squared, where you usually use x rather than z, about the origin, which we call Maclaurin series, is to keep differentiating and then plug in the point that you are expanding about. And there's a lot of waste of energy. So notice we did not, or we will not, fully utilize the functions save evaluating at z equals z0, which is 0. So all these functions, you spend all this energy making huge expressions. Now at the second derivative is already so big. I'm not going to switch Wolfram alpha, but you can play with it if you have a fast finger. Look for the 10th derivative of 1 over 1 plus z squared. It will be an amazing expression that you know you've chosen the right thing to do. Use the computer rather than your head. So you won't do it, okay? Then how do we go about doing it? Now the Taylor series is actually a special case of what I call the Weierstrass fundamental theorem. I want to convey the idea not that it's the fundamental theorem historically, but that's the fundamental idea that Weierstrass think of analytic functions. So you always think of it as a power series. And from last time to when we apply the power series with the coefficients and the Cauchy integral formula, he discovered that if you pose a power series representation inside a circular disk, then the coefficient has to be the Taylor coefficients. So he reversed the problem. Rather than looking for the Taylor coefficients by differentiation, whatever way you use to figure out power series representation, you can go back and then say that they're the same thing. So here's the method. So instead of doing this, always start with an easy one. Then manipulate the series. Equations. They're not really equations. Okay. So what is an easy series? An easy series is the geometric series. Okay. So let's look at this. 1 over 1 minus z. Anybody who can tell me immediately what this is? This will be critical for your next homework and quiz. I think that's the last one. 1 over 1 minus z. This one series that you need to memorize. What's the answer? There's several ways to remember it. Okay. The first way is if once upon a time you memorize the geometric series, have any of you ever remembered the formula for this from discrete math 150 or earlier? Yes, the x is r, right? So it tends to just a over 1 minus r as n goes to infinity. The same formula works. So use it in the opposite way. So that was the geometric series. There's no margin of error now because I can't switch tools. So a equals 1 and replace r by z, whatever is true, formula that's true in the real line should also be true on the complex plane because the complex plane covers the real line. So what I would do is to use a equals 1 and r replaced by z formally because that was not the original intention. But the correct answer is this: 1 plus z squared and so on. So in the summation notation, it is the summation of z to power n, the power function, without any extra coefficient. So that's method little one. The next method is also what we use for other series, is to do a long division and pretend z tells you the place value. So you have this 1 of 1 minus z, and you get z here. Then this will be plus z, and then you have z minus z squared, and then do subtraction. So whatever is empty there means 0. And so you go down, you get z squared, and then this plus z squared, and so on. I think you can quickly see that there's a pattern. The remainder is always just the same kind of power function, but with the exponent one higher. And so the quotient has that pattern. All right. So this algebra is well and good, and that's also what Euler proves, except later on, in the times of Weierstrass, people changed their habit to add one thing. To always add one thing rather than just writing this down. What's that one thing that you need to write? Felix, this is important. There's some missing detail here that you didn't write. What is that? So once you see this infinity, whenever you see infinity, it's something out of reach in normal logic. You have to pass through some definitions to actually derive what the limit is. Okay? And those theorems, limit theorems or convergence properties, uniform convergence, that kind of theorem. So here, convergence is a concern here. So what should we state to make sure that what I write is correct? No idea? So remember that. Radius of convergence. Okay, which is valid for all the always general form is the radius. Okay, now we are centered at 0, so I just write z modulus to be less than the radius convergence, and the radius convergence in this case is 1. And for this one is one of the quick way to recognize what the radius convergence is without actually calculating or proving whatever, is to look for where you have the division by 0. So in fact, a lot of those exceptions, all the way from the beginning to the logarithm, multi-valued, all of them, can be ultimately traced back to division by 0. So if you see division by 0, then it's not going to be inside the radius of convergence. So in this case, you maximize as much as you could, and z has to only up to modulus 1. Okay? So even though (1 over 1 minus -1 equals 1 over 2) is defined, but 1 plus z squared and so on is unable to represent um, 1 over 1 minus z at z equals -1 because the modulus is 1 and it is not strictly less than 1. Okay, so this is a lesson to be learned. If you try to break it and plug in z equals -1 on the original function, you get 1/2. Very nice, lovely value of a half. But imagine what happens when you put z equals -1 into the power series. What you get is 1 minus 1 plus 1 minus 1 plus 1. Do you say that converge? Okay. So students of real analysis are not surprised anymore because you have been playing with all kinds of crazier stuff. Okay. It is not converging at z equals -1, even though on the other side of the equation it does make sense. Okay. So the key thing is outside of the radius of convergence, there's no longer guarantee of convergence. If convergence is not guaranteed, then they might not be equal. Sometimes it's undefined. Okay, so we stay within our radius of convergence, and so we always. I can't change my tool. Okay, sorry. So let's just keep going. So that's our starting point. So what can we do? Using the standard geometric series is for manipulation of series. We can, the first thing you can do is substitution. Okay, and just like any algebraic theory, all the way back to even the theory of statements in logic. So you can substitute a variable by another variable. And the way you substitute it doesn't mean that you just change the name. You can even substitute an expression into it. And that's what we'll do now. So this is the technique A. So to obtain 1 over 1 plus z squared from 1 over 1 minus z, we can make the substitution u equals negative z squared into, so let me write it more verbosely. So first I have to replace the temporary variable. I have got a series that works, and for general radius convergence 1, and that variable I need to change. I use it as a theorem, and variables in the theorems are public variable you should change when you apply it. And here 1 over u was 1 plus u squared plus u cubed. I prefer to write this form for the intuitive appeal, and that is valid for the module less than 1. So then this substitute u equals negative z squared. You need to substitute both sides. So Felix, look at this carefully. You substitute 1, 2, 3 expressions. So two sides of the equality and then the radius of convergence statement. So what you get here is 1 over 1 plus z squared on the left. And on the right, you get 1 minus z squared plus z to the power 4 minus z to the power 6 plus and so on. Don't forget the last thing, and you say plug in negative z squared into the modulus, but then the things cancel and you get modulus squared less than 1. And that's because negative z squared modulus equals to the modulus of z squared and equals to the modulus of z, then take square. Properties are the same with absolute sign. So if you have a modulus which is a non-negative value squared less than 1, then if you put it back in the original, just the z modulus, what's the inequality? Now for real values, you could have, so pretending this is r for the module of z, you have r squared less than 1. So the usual way, the usual rule to solve this inequality is r squared less than 1 implies r is between -1 and 1. But here r cannot be negative. Okay? And so therefore, the final answer is this. So I repeat the right hand side, and then I need to do a negative power to some power, and I have 2n here. I think I can start from n from 0 to infinity, and the first one is going to be positive. and then this is valid for just the modulus of z less than 1. Agreed? So that's the first example. So calculus students are happy, vice versa are happy. All the technique you have learned is useful and it can be expanded to a huge amount, okay? Provided you restrict your attention to circular regions. Now this is the first one. So this is the answer. That is the power series for that. And we can use this already to do something that is start to give you some surprise. So let me put in an extra thing. Now the second technique that you can do and that you have seen before, another technique they can do after the substitution, and that has to be guaranteed by theorems, is technique number B, differentiation and integration term by term. And the radius of convergence do not change if you follow strictly inside. In the textbook, you will see, for the sake of proving it, some compactness needs to be assumed. So I'll give you a quick note here. The theorems have the form that this 1 over 1% apply to a function valid for the module of z less than or equal to R1 strictly less than 1. And those theorems are posed this way so that they can use something like a closed interval. So our closed interval is the circles with the boundaries included. Okay, and so for the sake of all those proofs, you will see an extra restriction here. But this R1 is for any R1's less than 1. That theorem can be proved. So if you talk about one particular fixed value of z that is inside a unit circle, you can always find a radius R1 that gives you a slightly small circle and closing it. So let me write that down. So for any z satisfying the modulus z less than 1, so you have this unit circle. This is 1 and this is I, so this is your z. There exists R1 less than 1 such that z also belongs to the disk center at 0. So then I have another one here with the boundary included, and the radius is R1. My circle is like an egg, but then it's not halved by the axis, and I can't correct it. Okay, I should do some copybook exercise this summer. So, okay, you get it? They should be circles, and the line is cutting it in 2 halves, but they don't look like 2 halves. Okay, next. So the theorems that you see from textbook might confuse you. It's not a huge concern to you. Whenever z you choose for that region, you can go back and pick an R1 big enough so that it's covered, so that it will work. And so in terms of algebra, if we integrate term by term, then starting from 1 over 1 plus z squared, I change to u squared, temporary, and then summation, negative 1 raised to the power n, and then z to the power 2n. Sorry, I made a big mistake here. This should be u. And then n from 0 to infinity. So that's what we have above. Okay. This I should put a line here, z. Oh, I think I copied one thing less. That should be a valid for something, but I'm going to integrate from 0 to z dz, integrate from 0 to, not infinity, z dz, and this will still be valid for the same radius. Okay, so if it's valid for the same radius, then what you get here on the right hand side is the summation n from 0 to infinity, assuming you can switch the order, even though it's infinitely many, not dz, du. Okay, so integrating u to power 2n is super easy, right? So you get summation n equals 0 to infinity, and then you have -1 to power n, and the power after 2n is 2n plus 1. So bring the 2n plus 1 down, and you get z to power 2n plus 1. The choice of the lower limit 0 is so that I don't have any left over. So I plug in z equals 0, a equals 0, so it doesn't add me any term here. Okay, so that is the result of the term by term integration on the right hand side. So you either write it in the pattern with the ellipses. So the first term, second term, third term, fourth term, plus the general term or general pattern. Integrate term by term, write the integrated sign many times. Or here, finally, the summation sign has some use. You write down a general term, and you only need to write down integrated sign once, okay? And integrate the general term directly. Remembering n here is just a general integer running from 2 to infinity. If your integration formula works for general integer n, actually non-negative integer n, then it should work. And happily, it works even for the case n equals 0. So when n equals 0, it's not the same kind of function, it's constant. But still it works. Okay? So this is on the right hand side. On the left hand side, what's the answer? Calculus students. What's the integral of 1 over 1 plus x squared dx? Can you remember that? Brian? Felix? Yeah, it's arctangent. Okay, so here you have this arctangent. So I should write this. So for a certain branch. So that is not what we want to be too worried about taking a branching. So in the real line, restricted to the real line, you get the usual arctangent of x equals summation of this x to power this, which is, if you plug in the formula, it will be, the first one will be x, the next one is x cubed over 3, and the next one is, so if you plug in n equals 2 here, you get the next odd number, which is 5, and then plus sign. So, and then the next term here, remember 2n plus 1 are the odd number sequence, right? So the next one is 7, and with that side. Okay, and this is the lesson here. This would not have been possible other than just pure guessing if you do Taylor expansion. So either you go up and do all these differentiation, because even for the derivative of arctangent, the first derivative will be already 1 over 1 plus x squared. And you differentiate again, you get this minus 2x over 1 plus x squared all squared on denominator. Repeat, repeat, and repeat. So either you write down the general formula for the nth derivative and evaluate at 0, or you find other means, okay? But in complex variables, the standard way is to start from the geometric series, substitution, and then integrate. Then you get the formula for the arctangent series. Okay? And you use this to estimate pi. For example, how can you estimate pi? Let's do the standard one, pi over 4. So arctangent of what is pi over 4? Arctangent means the inverse of tangent in a triangle. So if you look at pi over 4, it looks like this. Right? These are the same. So tangent is opposite, right, versus adjacent. For isosceles triangle, the ratio is 1. So pi over 4 equals arctangent of 1, and now you have this 1 minus 1 over 3 plus 1 over 5 minus 1 over 7, and so on. And ladies and gentlemen, I made a mistake. Where is it? You have to remember this. I made a mistake again. Same. I'll keep repeating that. What's the mistake? Yeah, that's the mistake. Felix, what's the mistake? If you write this in the quiz, you won't get full credit. Why? Now the powerful formula is correct. Okay. The line previous to it is incorrect. Not incorrect, it's correct, but you're missing a crucial thing. And when you read that crucial thing, you realize that the deduction is not really a deduction. What was missing? What was missing? You have to write that. What is missing? I write out the power series expansion of arctangent x. Now I restrict to the real line. So that is a complex number z. So I use modulus to indicate the region where the complex power series is valid. But for this case, what do I need to do? Right? What did I miss? Just guess.
Does it have something to do with the denominator?
No. The algebra is perfect. Come again. What's missing here compared to two lines?
They're valid for something.
Yes. And now that I've given such a big hint, you should continue. What should I write? Valid for? For what? Now, instead of a complex number and a modulus less than 1, what should I write? Now I have a real number x.
Mm-hmm.
What is the inequality that I write for x?
Can't be less than 1.
X what? Can't be less than 1?
Yeah, since I don't know, I just look at the shape and it's insane.
Yes, so the absolute value of x less than 1.
Yeah.
So is there another way to write it? I think people prefer to use double inequality to indicate absolute value of x less than 1. That's more intuitive because it tells you the interval rather than making you calculate absolute values. What is the interval where x can be in? So this is correct, which this is true if and only if for what interval? If and only if x is between x and -1, right? X is between -1 and 1, right? So valid for the interval -1 to 1. What did I do? By plugging 1, it does not imply this formula because x equals 1 is not inside the interval. So that's why the people taking 323 had extra work to do. At the boundary point, we cannot use it. Power, ratio test, all those things does not work. So you have to separately, just for that one single point, do a different kind of analysis. And this would come by, thankfully, alternating series. Happy, okay? Now, next example. Example number 2. I don't remember the exact thing. What was that? 1, 2, and then 3, 5. Okay. Expand. Z, and then 3, 5, about Z naught equals 0. How can we do this? So the only trick that we have is start from geometry series, make substitution, and then integrate or differentiate. And for this one, looks quite complicated. Okay, so let's do some investigation. So first off, relying on the memory of what we have seen, I think factorizing the denominator can help a little bit to see, okay, we've got the 1 plus z squared we've seen above. So we might be able to reuse it. Does it make sense? But it's not just 1 over 1 plus z squared. You have something on the denominator. Okay? So if you separate into two parts, then you get here 2z squared over 1 plus z squared. So we have recovered our previous knowledge. We have
what happened to the z cube on the second one?
Yeah, it should be here. Thank you. Okay, let me write that again for the sake of clarity and peace and joy. Let's write it again. Okay, now there's no mess. Now we want to reuse 1 over 1 plus z squared. Okay, and I haven't started writing where is the value. Once you do the replacement, you also bring in the replacement of the domain. Right now, I did not write down what domain it is. Okay, but once you do the replacement, the restriction is here. I did not analyze the zeros of the denominator. Okay, which you should be careful about. If you put in z equals 0 here, something is wrong. Okay, but let's work on it formally just to teach the techniques. So here you have a multiplication of 1 over z cubed and then 1 over z. So technique C, you can shift. I think computer scientists like to shift. So shift left and right. Using shifting operator is the most meager way to do some change to your code, okay? Rather than doing addition multiplication. Just shift the bit. And this is shifting. If you have z to power n times some c0 plus c1 z1 plus c2 z2 and so on, the shifting allows you to go this z power n plus c1 z power n plus 1. So don't look down upon this. We're still talking about infinity. Okay, and here is with the same domain of validity, and in summation form, you get this z to power n summation cn z to power n, and I should not use n. So let me change it to m. So here is a more general thing. Now you see, when I shift to the negative index, it is no longer a Maclaurin series. So up here, this can still be called a Maclaurin series. Can be a Maclaurin series for the first one. This one cannot be a Maclaurin series. And the reason is because you start from a negative index. Okay? So when you plug in z equals 0, it does not work anymore. So, but this technique of shifting indices actually works even if you have negative integer powers. So fractional powers, I don't talk about it. But integer power, it still works. So instead of starting from 0, I'm going to be audacious and simply say start from negative infinity all the way to positive infinity. This will work. And this is valid in an annulus domain. And that annulus domain is like r, little r. I don't think I should use little r. Let me think. Can I use? Yeah, I'm not using r too much. Let's use little r. And then the modulus of z, and then less than the greater r. So you cannot include the case when r is 0. Actually, you can include the case r equals 0, but you cannot include the case z equals 0. So this r equals 0 and greater r equals positive infinity are both possible. But z equals 0 is disregarded. You should treat it separately. And z equals 0 is the singularity. Okay? But this form of series intentionally avoid talking about it by the algebraic form. So if you have r equals 0, because of the strict inequality, you don't actually hit exactly z equals 0. So you avoid it. So this is going to be generally valid. You can have r equals 0 too. So let's look at what we have here. So let's repeat it. So back to the calculation. The calculation was 1 plus 2z squared, 1 plus 2z squared over z cubed plus z to the power 5 gets simplified into 1 over z cubed, 1 over 1 plus z squared, plus 2 over z, and then 1 over 1 plus z squared. Okay? So you have this shifting. If I write it in the full form, I think what we had was 1 minus z squared plus z to the power 4 minus z to the power 6, and so on. Let's write more terms. At 2 over z times 1 minus z squared plus z to the power 4 minus z to the power 6 plus z to the power 8. So we're allowed to do this shifting. And so we will start from 1 over z cubed minus 1 over z plus z minus z cubed plus z to the power 5 minus a big pile of things plus down there I got 2 over z minus 2z plus 2z cubed and then minus 2z to the power 5 and then plus and so on. Okay? So sometimes what you really want to know is not the full form. Okay, you can go back to the summation sign form that I gave and try to combine the coefficients. You can do it, but that I don't do. Here I'm going to write down the first few terms, and the leading terms I'm going to arrange in the same order as I write here, and then minus 1 over z. Oh, but plus 2 over z, so I get a cancel a little bit. So I get 1 over z cubed plus 1 over z. That is the most important term I want to know. And sometimes that's the only term I care. And the next one is minus z, and the next one is plus z cubed, and the next one is minus z to the power 5. Very nice pattern, but you try to figure out, okay? Try to figure out the rest. First off, let me repeat the question. What have I missed? Felix, what have I missed? All the algebra here is good. I know these new kind of algebra will take up a lot of memory. Okay? But there's an easier part that is not about the techniques that you need to remember. And that is, what is it, Brian?
The radius of origins.
Correct. Okay, but we have to change the name a little bit because it's no longer just a circle. We have two circles. We have the outer circle, we have the inner circle. So there's an outer circle of radius r, and then there's this tiny little inner circle radius little r. And what we're talking about is the donut that makes you hungry. That makes you remember that you haven't had your breakfast. Some of you, or me. Okay, so that's the annulus region or donut region. It's not just one radius, there's two radius. Okay? In this case, I've never mentioned it. When is it valid? So the original one, this part, let me just call this 1 over 1 plus z squared equals 1 minus z squared plus z power 4 minus z power 6, and so on, is valid for the modulo of z less than 1, right? And once you have a shifting here, you will take the most restrictive version. When you do the shifting, 1 over z cubed actually is not valid everywhere. So treating this as a series, so let me put it here, because I can't easily change my tool. 1 over z cubed can be recognized as 1 over z cubed plus 0 over z squared plus 0 over z plus 0 plus and so on. Plus, I should write 0z and then 0z squared and so on. Make sense? So in Weierstrass analytic function theory, everything is a power series, including positive and negative powers. So when you have even a very simple function 1 over z cubed, you recognize it as a series. And this one is not harder than before to recognize what's the reason. It's just weird, okay? You have a very strong memory, muscle memory of how you work with this. But if you recognize it as a power series with negative powers, it's not going to be everywhere valid because that's a singularity, right? So this one is valid for the values of little r equals 0 and the upper r equals infinity. It looks like I have not restricted anything, but yes, I did. Okay, you excluded the points that equal 0 by this inequality. Only 1 point. All good? So once you have that, then oops, what happened? Once you have that, then you need to superimpose the two restrictions. Where am I here? So here, once you do the two restrictions, this is going to be valid for 0 less than this. Copy again. Valid for 0 less than the modulo of z less than 1. And this is valid for 0. And the implication of this is that once you check the validity, you can do a contour integration, C R plus 0 of this whole thing was 1 plus 2z squared over z cubed plus z power 5. Very ugly thing. So you can use contour integration over two sides using your representation and using your memory from what you learned from activity, the new activity for topic 7. The right hand side is super hard to integrate, that rational function. But once you have the power series representation, and from what you have learned from that activity, only this term is useful. Everything else vanishes by Cauchy's trick. So the answer is going to be, this part is going to be 2 pi I. But there's a restriction. This works only if your r is less than 1 and greater than 0. So if you do a contour integration with the contour, a circular contour that goes outside of that annulus region, or the punctured disc, some people call it punctured disc because there's only one point that's excluded, then you cannot do it. You need to use different representation. And the coefficients will change, as we shall see in the next examples. Okay? So that equality that you get is valid only when your module of z is between 0 and 1. Okay, so now example number 3. Yes, that's exactly what I want to do. 3 over 2 plus z minus z squared. I already forgot.
3 over 2 minus z.
Thank you.
Plus z minus z squared.
Okay, not too bad. So expand this about. So now that you have it, Miriam, can you also tell me the little wording I wrote about R? Did you scroll up to that? Because I'm not just expanding this. I have the choice, valid for something.
Inside r equals 1, between r equals 1 and r equals 2, and outside r equals 2.
Thank you. There's 3 cases. Okay. Now things start to get mysterious. Okay. And really writing down the validity is gonna be a survival technique on this one. If you don't check the validity, the calculation will be gone. And thinking 3 parts, you only get 1 part correct, depending on the luck. Okay. So 3 over 2 plus z minus z squared seems to be easier. Okay. So how are we gonna go about doing that? Well, before we do that, let's do a very quick sketch. Look at this. 2 plus z minus z squared. What is that? Let me write it in a more helpful form. Z squared minus z minus 2. Does it ring a bell? Can you factorize that? Right? Z minus 2, z plus 1, right? So factorize it. Z minus 2, z plus 1. So if you were to sketch it, because that's the 0 of the denominator, it will be a singularity of the original function. And the forbidden points are -1 and +2. Okay, so -1, +2. So you see the purpose of the cases down there. We have to avoid singularity. A power series, even with negative powers, is going to be converging. It should converge for every point inside the defined domain, whether it's a disk or annulus. Okay? So if you have an annulus region or this region that includes some singularity in the interior of it, then you must be wrong. That's a quick way to tell you must be wrong. So you have to choose some disk and some annulus region so that they are avoided at least by the boundary of it. So the first case is here. Use a unit disk. This is case number 1. Case number 2, you can use an annulus region. And then you have both singularity. Avoid it at the boundary. And the last case, take the outside of it. So in all 3 ways, you get valid expansions, avoiding the singularity. You have to. Okay, so let's quickly show how you can do that. So for case 1, you are choosing manipulation using technique that we have seen above, but maintaining the z to be less than 1. This is the easiest case. So if this 3 over 2 plus z minus z squared. So how do you do this? You want to use power series? How do you do that?
You factorize the denominator and then multiply and you get the expansion.
So if you factorize like that, oh, that's a good idea. So you have, if I put it inside there, I have 2 minus z, 1 plus z. I plug in the negative sign into one of the factors. Okay. How to multiply? What are we going to do? So we have a product here. We have a product here. What are we going to do?
You have 1 over 1 plus z.
And then we put it in the other side.
If we separate them into
You can get power series for each one, but I was going to maybe combine the power series, multiplication in power series.
Should we do that? It looks like Finian doesn't like the idea. So let's do exactly that. So okay. So what we're gonna do here is the crazy idea of multiplying 2 power series, and he can foresee something ugly happening. Okay, but at least the power series we're multiplying isn't that bad. And you have 1 plus z squared plus z cubed, and so on. And now I have to do the quick check of validity. This is valid for, I did a substitution quickly. So I'm using the power series for geometric series with the variable z over 2. Okay. And the other one is valid.
Why is it all sums? Should it not be 1 minus z plus z squared minus z cubed plus...
You mean alternating?
Yeah,
For the second one, yes.
yeah.
Yeah. So with the simplification of the validity statements, you get it valid. For the more restricted one, and the more restricted one is the one on the right. So we're good. So we are. This method will achieve our goal. And here is the fourth technique. So this is valid for the module of z over 2 less than 1, and that one's modulus of negative z. So the negative sign can go away. And technique D is the product of power series. Really? Seriously? And that's called Cauchy product. There's a name to it. There should be something good coming out of it. So the Cauchy product power series. So what does it mean? Go ahead. An rather than center at z0, just use z to the power n. Yes, you can do that. It converges. Okay, but but the form of it is ugly. So, okay, valid with a radius of convergence that is the smaller one. Of those of the two original series. Okay, so that's the next technique. So let's, without further ado, look at this, and then I think for a given time I won't go to example number 4. Give you an extra video to watch. Okay, but this one I would go to talk about Euler's Basel problem from this. People before the development of linear analysis and complex analysis have been doing all these addition, subtraction, multiplication of infinite many terms all the time, until people are fed up with it, with all the convictions that could come out. But we're in a safe place. We have all these things cleaned up, and these are valid. Okay, as long as you're within the region of validity. So collecting terms. So in this case, if you temporarily ignore the dot dot dot, it's not that scary. Okay, if you're only asked to provide the first 4 or 5 terms, it's not that scary. To write out a general formula is a different issue, which maybe Phineas is trying to think about that. So let's just write the first 4 to 5 and choose that. The constant term has to be Chen. It's very clear. There's only one possibility here for the constant term. Correct. Okay. So favorite 2. And then Felix, let's try. The linear term, the coefficient of z. How can you obtain that? So choose one term from here. That would possibly give you the term with z. Which term can you choose? This one? If you choose z over 2 here, then on the right hand side, which would you choose to multiply? Because of distributive law, you have to choose one of them. So if you choose z over 2, then you have to choose so that the product is a linear term, a z to the power 1 term. So among these terms, 1, negative z plus z squared, negative z cubed, which one can you choose to multiply to this one, z over 2, so that you get a summing times z? There's only one choice. Among these 4 terms I show you here, which one is the choice? Multiply to z over 2. Negative z? If you do negative z times z over 2, you get negative z squared over 2. I don't want a square term, I want a power 1 term. So if you have chosen z over 2, then you have to choose you have to choose 1. Z over 2 times 1 gives you something times z. But there's another choice, okay? If you choose 1 here on the left, because distributive law, you choose 1 term from each bracket. So distributive law, you choose 1 term from each bracket, 1 term from each bracket, multiply. And then gather all the terms. That's how you do distributive law for many terms. So if you choose 1 here, what should you choose for the other one? To get a power of z to the power 1. So if you choose 1 here, what do you choose for the other bracket? Negative z, right? I heard you said negative, right? Negative z times 1, so you get negative z. And then don't forget the 3 over 2 in front. That is the correct answer. Okay? And that's exactly what the Cauchy product is saying. You have this sum for the n to power 0 term, you get the sum from k to 0 to 0, 1 term. But when you have z to power 1, you get 2 terms because you have the index k goes 0 and k goes 1. And then if you have the next one, you have 3 terms, 4 terms, 5 terms, and so on. So for the product series, while sometimes it's impossible to write out the full formula, at least you have a more abstract formula you can write down, pass it to a for loop, and we'll actually do that all the time. Okay? But for us, a lot of times we just want first few terms. So if you multiply these, and run out of time, the z squared, if I want to copy the coefficients, I should have 1/4 here, 1/4 times 1. And the second way I can do a quadratic term is to do here z over 2 times negative z. So I get minus 1/2. And the last term is 1 times the positive z squared on the right hand side plus 1. And that's z squared. And the next one is just 4 terms. So I have 1 over 8 and then minus 1 over 4 plus 1 over 2 and then minus 1. You can see a pattern here, which I won't pursue. Okay, but things can cancel, and then so here that was 1/2 minus 1, so it's negative 1, so it's minus 3 over 4 z, and this one is 3 over 4, so 3 over 2 times 3 over 4 z squared, and this term is 3 over 2 and then plus 5 over 8 negative z cubed is alternating. And this is valid for z less than 1. Okay, so let me quickly show you because time's running out, Euler's solution to the Basel problem. Also uses similar idea. Formal multiplication of infinite series. With an extra idea though. So look at this, the problem sine x over x, we know that what we have just learned by shifting, you get this x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial, and so on. Okay? And of course, he did not have a lot of regard for the validity. Of course, he just say, okay, x is not equal to 0. That's it. Okay. But if you allow the redefinition of that point, you on the right hand side, you actually see this. So here we know that x equals 0 is a removable singularity. Because on the right hand side, looking at the expansion, there's no singularity at all. Okay? On the left, it appears that there is division by 0, but on the right hand side, you see that it does not in this representation. Note that x equals plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on, are the roots of sine x over x. X equals 0 is included because if you plug in x equals 0 by in limit equals 1, it's not root. But for everything else that was original, the roots of sine x, they really are roots. Plug in sine pi is 0. So 0 over pi is also 0. Then, pretending the right hand side can be factorized, indefinitely, then you get sine x over x equals x minus pi, x plus pi, x minus 2 pi, x plus 2 pi, x minus 3 pi, x plus 3 pi, and so on. Okay. And now the last step is to consider the x squared term. On the left hand side, it is negative. On the left hand side of this, it is the negative of 1 over 6. On the right hand side, which is the new factorization, how do you get the powers so you will just choose let me make it simpler, x squared minus pi squared, x squared minus 2 squared pi squared, x squared minus 3 squared pi squared. If you look at the power of x squared term, first combining this, then we get pi squared times 1 times 1 times 1 times 1 times 1. If you get an x squared term, you want it 1 times that, and so on. So you get, eventually, what I want to show is it should be summation negative 1 over n squared pi square. I think my memory is fading here. I'll write down the correct answer for you. 1 to infinity. So in other words, 1 over 6 equals summation pi square over n square, n equals 1 to infinity, or the summation of 1 over n square, n from 1 to infinity, equals, I think this is over 1 over pi square here. It's pi square over 6. So that mysterious series, people love sum of squares from ancient Greeks. The inverse of it, the answer is pi square over 6. That's the Basel problem. Formal expansion of products indefinitely. Okay, so we'll come back to this after the Easter break. There's a couple of problems that I didn't reach to. It's just the names here. So I will tell you the names, but you can feel free to skip it and wait until I come back. We come back to the next class to actually do it. So here, this z equals 0 has finitely many negative powers. So this is a pole. Okay. So if you have a power series expansion that has a few negative powers, it is called a pole. Okay. And in the one that I've just shown, in the power series expansion, it has no negative powers down here for the Euler's one. This one, this singularity x equals 0 is a removable singularity. So that is done in quiz number 4. And then for this kind, sine over 1z, which is going to be reversing it. So with over 1 over z plus, minus 1 over 3 factorial, set to power minus 3, plus 1 over 5 factorial, set to power minus 5, and so on. It has infinitely many negative powers. Then in this case, z equals 0 is called an essential singularity. So in summary, let me write it down at the very beginning, at the very bottom, just a few names. We have already recognized it. Oops, I shouldn't have do this. So the very last thing is that if f is not analytic at z equals z naught, then z naught is called a singularity. And if it is isolated, meaning that the distance from this singularity to the next singularity is not 0, okay, then you have 3 cases. The first case is removable, the second case is a pole, and the third case is essential singularity. Only these 3 cases. And in the course of doing all those power series manipulations, wherever you see some negative powers, it's a pole. If you see no negative powers, it is actually removable. If you see infinitely many negative powers, that is essential singularity. Okay, just a name for that. See you next time. So let me stop the recording and fix the notes. And the last one, the Euler solution to the Basel problem, is for fun. Okay, don't worry too much about it.